Exponential functions. Let's try to compute the derivative of the exponential function using the definition f of x is equal to a to the power of x of a derivative. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h, which is equal to the limit as h approaches 0 of a to the x plus h minus a to the x over h. So if we take a look at this first term, a to the x plus h, we can rewrite that as a to the x times a to the h. So the limit as h approaches 0 of a to the x times a to the h minus a to the x over h. And what that allows us to do is then we can factor out the a to the x. So we have the limit as h approaches 0 of a to the x times a to the h minus 1 over h. Now, the factor a to the x doesn't depend on h, so we can take it in the front of the limit. So this becomes f prime of x is equal to a to the x times a limit as h approaches 0 of a to the h minus 1 over h. Now notice that the limit is the value of the derivative of f at 0, and that is as the limit as h approaches 0, we get a to the h minus 1 over h because a to the 0 is equal to 1. So a to the h minus 1 over h is equal to f prime of 0. So therefore we have shown that if the exponential function f of x is equal to a to the x is differentiable at 0, then it is differentiable everywhere. And therefore that gives us definition number 4. F prime of x is equal to the derivative with an input of 0 times a to the x. This equation says that the rate of change of any exponential function is proportional to the function itself. The slope is proportional to the height. Numerical evidence for the existence of f prime of 0 is given in the table here for the cases of when a is equal to 2 and when a is equal to 3. Now, values are stated corrected to 4 decimal places, so it appears the limit exists. So here we have h going from 0.1, 0.01, all the way to close to 0 as we can. We plug in 0.1, we get 0.717. If we plug in 0.1 for 3 to the h minus 1 over h, then we get 1.16.2. And as we keep plugging those numbers in, getting closer and closer to 0, we can see that when we plug it in for the 0 in the function of the limit as h approaches th minus 1, 2 to the h minus 1 over h, gives us approximately 0.69. And when we use the value of a to be 3, the limit as h approaches 0 of 3 to the h minus 1 over h is approaching approximately 1.10. So in fact, it can be proved that these limits exist and correct to 6 decimal places, then the values are the following. The derivative with respect to x of 2 to the x as x is equal to 0 is approximately 0.693147. The derivative with respect to x of 3 to the x when x is equal to 0 is approximately 1.098612. So, in definition number 5, we say the derivative with respect to x of 2 to the x is approximately 0.69 times 2 to the x. The derivative with respect to x 3 to the x is approximately 1.10 times 3 to the x. Now, of all possible choices for the base a in equation 4, the simplest differentiation formula occurs when f prime of 0 is equal to 1. In view of the estimates of f prime of 0 for a is equal to 2 and a is equal to 3, it seems reasonable that there is a number a between 2 and 3 for which f prime of 0 is equal to 1. So it is traditional to denote this value by the letter e, and in fact that is how we introduced e in section 1.5. Thus we have the following definition. The definition of the number e. E is the number such that the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. So, geometrically, this means that of all possible exponential functions y is equal to a to the x, the function f of x is equal to e to the x is the one whose tangent line at 0, 1 has a slope of f prime of 0 that is exactly 1. So we can see that in this figure below here. So therefore, here's our three graphs. We have y is equal to 3 to the x, we have y is equal to 2 to the x, and then we have y is equal to e to the x. So it's in between those two exponential functions. Now, if we take a look at the value at 1, we can see that the slope is 1 for y is equal to e to the x. And then if we pick a point here, which is x e to the x, then the slope is equal to e to the x. So the derivative of the natural exponential function tells us that the derivative with respect to x of e to the x is going to equal e to the x. Thus, the exponential function f of x is equal to e to the x has the property that it's its own derivative. The geometrical significance of this fact is that the slope of the tangent line to the curve y equals e to the x is equal to the y coordinate of the point, which is up here.